When I talk about the beginning of everything, I like to imagine that I am holding a remote control for the universe itself. Not just for a film about the universe, but for the real thing. I press pause on the present moment, on this quiet instant where you are listening, breathing, maybe starting to feel your eyelids grow heavy. Then, with a small movement, I press rewind. At first, nothing seems different. The nearest stars in our night sky barely shift. The planets continue their gentle dance around the sun. But then, slowly, the motion becomes obvious. Galaxies that we know are drifting apart in reality now seem to creep toward each other. The great spiral of the Milky Way folds inward, as if someone is pulling on every arm at once. I keep rewinding. Clusters of galaxies that once spanned tens of millions of light years begin to shrink. The dark gaps between them, those vast cosmic voids, narrow. The graceful web of matter that stretches across the cosmos, with its filaments and knots and empty spaces, tightens like a net being drawn in from all directions. Space, which we usually think of as the stage on which things move, does not stay still. It contracts along with everything else. What used to feel enormous begins to feel confined. On smaller scales, the same rewind plays out. Stars that once burned for billions of years seem to inhale their own light. Their outer layers fall inward, their nuclear engines run backward, their fuel becomes untouched again. Planets leave their orbits, sliding back through long spiral paths into swirling clouds of gas and dust, as if entire solar systems are dissolving into the raw ingredients from which they formed. Asteroids, comets, moons, all the familiar furniture of a galaxy blend into a smoother and smoother medium. If I continue this mental rewind, the universe quickly stops looking like the one we know. There comes a time when there are no more galaxies at all, just a hot, dense soup of matter and radiation. Atoms cannot survive here. Every attempt of an electron to orbit a nucleus is undone by the fierce energy of passing light. The whole cosmos becomes a kind of glowing fog, opaque, restless, and unimaginably bright. It is no longer sensible to talk about night and day, about empty space and solid matter. Everything is compact. Everything is interacting with everything else. Further back, the picture becomes stranger still. Even the particles we are familiar with, like protons and neutrons, begin to lose their identity. The temperature and density climb to such extremes that matter dissolves into a mixture of more fundamental constituents. At this point, my imagination starts to protest, because there is nothing like this in ordinary human experience. I have to lean on equations and experiments and the careful work of generations of physicists to even give this state a name. It is a plasma of elementary particles, a phase where the distinctions that make our everyday world possible have not yet emerged. And then, in the strictest version of the story, something even stranger happens. If I take the mathematics of general relativity and the standard model of particle physics, and I trust them beyond the range where they have been tested, they tell me that if I rewind far enough, all of this shrinking does not stop. The density does not level off at some stable, finite value. It climbs and climbs until, in the limit, it becomes infinite. Space itself collapses into what we call a singularity, a point where curvature and energy density blow up without bound. Time, measured by any physical clock, seems to come to an end. That singularity is often treated, in popular language, as if it were a real physical point that once existed, where all the matter in the universe was squeezed into something smaller than an atom, or smaller than a grain of sand. But in the careful language of physics, it is more honest to say that the singularity marks a place where our current theories stop making sense. It is a warning light, not a photograph. When quantities go to infinity in our equations, it usually means we are trying to use a tool outside the conditions where it was designed to work. Still, for the purpose of setting the stage, it is okay to imagine that rewind sequence ending in a kind of luminous, impossibly compressed state, balanced on the edge of existence. This is what we label, somewhat poetically, as the Big Bang. Not a bang in the sense of a bomb going off in pre-existing emptiness, but a moment when every distance in the universe was smaller, every density higher, every temperature more intense, all the way down to a limit we cannot resolve. What matters for us now is that, according to our best observations, the universe has been expanding and cooling since that early hot phase. That is the part the evidence supports with remarkable clarity. Yet as soon as we put this picture together in our minds, a question appears almost automatically. If the universe has a finite age, if there was a time when everything we see was once crowded into a much smaller region, then what, if anything, was there before that? Was there a before at all? Is it meaningful to ask what existed when there was no time, no space, no matter in the way we usually understand those words? This is where the mystery begins to feel almost unreasonable. Our brains are trained from childhood to think in terms of before and after, cause and effect, past and future. Every event we know seems to have something that came before it. You were born after your parents met. The sun rose this morning after the earth completed another rotation. A glass falls after it slips from someone's hand. The pattern of time having a direction, of every moment following from earlier ones, is deeply woven into how we think. So when we are told that the universe itself had a beginning, there is a natural impulse to ask, all right, but what came before the beginning? One of the most challenging ideas in modern cosmology is that this question might, in a strict sense, be ill-posed. In general relativity, time is not a stage that exists on its own. It is part of the fabric of space-time, which is shaped by energy and matter. If space-time itself has a boundary in the past, if there is a point beyond which the concept of time no longer applies, then asking what happened before that is like asking what lies north of the North Pole. The words sound simple, but they hide a contradiction. North is defined relative to the geometry of a sphere. At the pole, that definition breaks down. You can stand there, spin in any direction you like, and you will not find a further north. The same may be true of time at the beginning of the universe. If the cosmic clock itself starts at a particular moment, then earlier is not just unknown, it is undefined. There is no earlier because there is no time for events to sit inside. That is the conservative view suggested by classical general relativity. In that view, the Big Bang is not an explosion inside an older, empty arena. It is the moment when the arena itself comes into being. I find this idea both unsettling and strangely calming. It is unsettling because it pushes hard against the way our minds usually link events together. It asks us to accept that some questions that seem natural to us do not actually correspond to anything in the physical world. It is calming because it means we do not have to imagine something out of nothing in the usual sense. The universe does not need a cause that operates in time before time exists. The rules of the game simply begin with the game itself. Of course, human curiosity rarely stops with the conservative view. Even while we respect the fact that our current equations break down at extreme densities, we also try to imagine ways they might be extended or replaced. That is where quantum gravity, cyclic models, and other bold ideas come in, and we will drift into those oceans later. But at this opening stage of our journey, I want to stay with the feeling of the question itself. The tension between the urge to ask what before and the possibility that before is not a meaningful word at the deepest level. As you lie there listening, perhaps with dim light seeping under a door or the soft hum of a fan in the background. You can treat this tension like a kind of mental cradle. On one side, you have the image of everything rewinding, collapsing, rushing back into a state so dense and hot that it defies imagination. On the other side, you have the whisper that time might begin there, that no hidden chapter lies behind that first page. Your thoughts can sway slowly between these two possibilities. Like a pendulum that gradually loses energy, its swing growing smaller and smaller until it comes to rest. You do not need to choose a final answer. Science itself has not chosen one. What we do have is a clear, well-tested story about how the universe has behaved since its earliest observable moments, and a set of deep, honest questions about whether those moments truly constitute a beginning or just a beginning of our current description. To sense the weight of those questions is already to participate in the work of cosmology. You do not have to solve the equations. You only have to let the ideas settle, like dust in a beam of starlight, slowly drifting down as your mind relaxes. In that sense, the greatest mystery of all is not only out there in some unreachable past, it is also right here, in the way a finite being like you or me can even ask the question, before the universe, was there nothing or something different or no time at all? I cannot tell you yet. But I can tell you that just by wondering, you are mirroring the very process that built the cosmos. Small fluctuations of curiosity, tiny ripples of thought, amplifying over time into galaxies of understanding. For tonight, that is enough. You can let the question rest beside you like a quiet companion, knowing that the search for its answer is still unfolding, just as the universe itself continues to unfold around you. When we talk about the beginning of the universe in a scientific way, we are not just guessing in the dark. We are listening to very old light, measuring tiny whispers in the sky, and reading the chemical fingerprints left in the first atoms. This part of the story is less about speculation and more about the quiet, steady work of building a picture from evidence. It is the part where we can say, with a surprising amount of confidence, what happened after the universe began to expand, even if we still do not know exactly how that expansion first started. The first thing to understand is that the Big Bang, as science uses the term, is not an explosion that went off at one point in space. It is the rapid expansion of space itself. Imagine a calm rubber sheet with tiny dots drawn all over it. If you stretch the sheet, each dot moves away from every other dot, not because they are rushing through the sheet, but because the sheet itself is expanding. In our universe, the dots are galaxies, and the sheet is space-time. When we look far away, we see that distant galaxies are redshifted, their light stretched to longer wavelengths, which tells us they are moving away from us. The farther they are, the faster they recede. This simple pattern is one of the strongest signs that the universe is expanding. From that expansion, and from the speed at which it is happening, we can work backwards to estimate how long the universe has been doing this. The answer we get, after refining our measurements many times, is about 13.8 billion years. That number comes from combining several different observations: the glow of the cosmic microwave background, the distribution of galaxies, and the brightness of certain kinds of exploding stars that act as distance markers. The fact that these independent lines of evidence all converge on the same age is one reason we trust the picture so much. Very early on, right after expansion began, something dramatic is thought to have happened. Over a truly tiny fraction of a second, the universe seems to have gone through a phase of incredibly rapid stretching called inflation. During inflation, according to the leading models, the distances between points grew faster than light could have crossed them. This does not break any cosmic rule, because what is limited by the speed of light is motion through space, not the expansion of space itself. Inflation is important because it explains why the universe looks so uniform on large scales, and why the tiny irregularities we do see have the pattern they do. Quantum fluctuations, small random jitters in the energy field that drove inflation, were blown up to cosmic size and became the initial imprints of structure. Once inflation ended, the energy stored in that field was released into a bath of particles. The universe filled with a hot plasma of quarks, gluons, electrons, neutrinos, and photons. This is a state we can, in a way, recreate in particle accelerators. A dense, energetic soup where particles are created and annihilated in a steady dance. In these first fractions of a second, temperatures and densities were so extreme that almost nothing we are familiar with could survive. This is where our knowledge leans most heavily on theory. But it is not theory floating free. It is grounded in physics, tested in laboratories, extended to conditions far beyond what we can reach experimentally. As the universe expanded, this plasma cooled. After a tiny sliver of time, quarks combined into protons and neutrons. That might sound like a simple step, but it is fundamental. Protons and neutrons are the building blocks of atomic nuclei, and their formation set the stage for the first real chemistry of the cosmos. After only a few minutes, when the temperature had dropped to a point where nuclear reactions could proceed, but not run wild forever, protons and neutrons began to fuse into heavier nuclei. This process is called primordial nucleosynthesis. During primordial nucleosynthesis, most of the protons remained as hydrogen nuclei, but a significant fraction fused into helium and a little bit into lithium and a few other very light elements. The exact proportions depend sensitively on the conditions of that early period, the density of baryonic matter, the rate of expansion, the balance of different particle species. When we look out today and measure the abundances of these light elements in the oldest stars and in diffuse gas clouds, we find that they agree strikingly well with the predictions of this hot early universe model. That agreement is like a fossil from a time when the universe was only minutes old, encoded in the chemistry of the cosmos. Even after nuclei formed, electrons were still not bound to them. The temperature remained high enough that any attempt to form an atom was quickly shredded by energetic photons. For a long time, on human scales at least, the universe stayed in this state, a hot, ionized plasma where light and matter were tightly coupled. Photons constantly bounced off free electrons, unable to travel in straight lines for any significant distance. If you could somehow have been inside that universe, you would not have seen stars scattered on a dark background. You would have found yourself in a bright, foggy environment where the concept of a clear line of sight hardly made sense. As expansion continued and hundreds of thousands of years rolled by, the average temperature of the universe dropped further. Eventually, it reached a critical point where electrons could finally bind to nuclei without being immediately knocked loose. Almost everywhere at once, protons and helium nuclei captured electrons and formed neutral atoms. This event is called recombination, though in truth it was the first combination of these particles, not a second one. The effect on light was profound. Once the free electrons disappeared into atoms, photons no longer scattered as they had before. They were suddenly free to travel vast distances without major interruption. Those newly liberated photons have been traveling ever since, stretching in wavelength as the universe expands. What began as a glow in the visible and infrared range has been redshifted down into the microwave band. Today, we observe this radiation as the cosmic microwave background, a nearly uniform bath of light with a temperature of about 2.7 degrees above absolute zero. It comes to us from all directions with remarkable smoothness. When we map this background with instruments in space and on the ground, we see only tiny fluctuations in temperature and polarization, slight ripples that correspond to regions of slightly higher or lower density at the time of recombination. These maps are extraordinary scientific achievements. They let us see the universe as it was when it was only a few 100,000 years old, a tiny fraction of its present age. From the pattern of ripples in the microwave background, we can infer the total amount of ordinary matter, the presence and density of dark matter, the curvature of space, and the overall rate of expansion. The fit between the observations and the simplest cosmological model, the one with cold dark matter and a cosmological constant, is remarkably good. It tells us that on very large scales, the universe is nearly flat, almost the same in all directions, and dominated not by the matter we can see, but by invisible components. After recombination, the universe entered what we sometimes call the cosmic dark ages. There was light, but it was the faint glow of the background, slowly dimming as space stretched, and there were no new sources of illumination yet. The neutral hydrogen and helium gas that filled space began to clump under the pull of gravity, guided by the deeper wells of dark matter, which had been quietly shaping the distribution of mass since much earlier times. Over tens of millions of years, small overdensities grew into larger ones. Gas flowed into these growing halos of dark matter, heating as it fell, cooling as it radiated, eventually forming the first stars. Those first stars, often called population 3 stars, were probably very different from the stars we know best. They are thought to have been massive, hot, and short-lived, burning out in just a few million years. We have not yet directly observed them, but new telescopes are beginning to probe the era in which they must have shone. Their light would have reionized the surrounding hydrogen, ending the Dark Ages and ushering in the epoch of galaxies and large-scale structure. By the time a few 100 million years had passed since the beginning of expansion, the universe was populated with the first primitive galaxies, small by today's standards but already forming stars at impressive rates. As more and more galaxies formed and merged, the cosmic web took on its familiar appearance: long filaments of matter, nodes where many filaments meet, and wide gaps in between. When we survey this structure today with large telescopes, mapping millions of galaxies across billions of light years, we see precisely the kind of pattern that gravitational growth, starting from the tiny fluctuations seen in the microwave background, would produce. We run simulations on supercomputers, starting with a nearly uniform universe sprinkled with small random variations, and let gravity, gas physics, and cosmic expansion do their work. The result is a synthetic universe whose large-scale patterns look remarkably like the one we observe. There is another, later clue in this story, one that is both comforting and slightly eerie. For a long time, astronomers assumed that the expansion of the universe must be slowing down over time, as gravity from all the matter within it gently tugged everything back. Then, in the late 1990s, observations of distant Type 1, a supernovae, special kinds of stellar explosions that serve as standard candles, revealed something unexpected. These supernovae were dimmer than they would be if the expansion was simply coasting or slowing. The best explanation was that the expansion of the universe has been speeding up for the past several billion years, as if some mysterious component with negative pressure, often called dark energy, is pushing space-time apart. This accelerating expansion is woven into the same cosmological model that fits the microwave background and the galaxy surveys. When we include a smooth dark energy component and a cold dark matter component, along with ordinary matter and radiation, we get a universe that evolves in time in precisely the way we see. On large scales, this model is not a story told for comfort. It is a network of equations that has been tested against a rich variety of data, relic light, element abundances, supernova brightness, galaxy clustering, gravitational lensing. The fact that one simple set of parameters can match so many different observations is one of the most striking achievements of modern cosmology. So, when we say this is what science knows, we are not claiming perfection or finality. We are describing a layered structure of understanding, anchored at many points by measurement. We know that the universe is expanding because we see the redshift of galaxies. We know that it was once hotter and denser because we see the cosmic microwave background and the light element abundances. We know that structure grew over time because we see its imprint at different distances, which correspond to different ages. We know that some form of dark matter is present because galaxies rotate too fast in their outer regions and clusters hold together more strongly than visible matter alone would allow. We know that some form of dark energy seems to be acting because the expansion is accelerating rather than slowing. You can think of all this as a kind of cosmic family album. Each observation is a photograph taken at a different time and from a different angle. Some are grainy and old, like the microwave background. Some are sharp and detailed, like images from modern space telescopes. When you spread them all out on a table, they tell a coherent story of growth and change. We cannot see the very first page in that album yet, the one that would show us exactly how expansion began. But from the pages we do have, we can trace the line of the universe's life with a clarity that would have astonished earlier generations. As you listen to this, perhaps in the dimness of evening or in the soft silence before sleep, it is worth letting that clarity sink in. The same laws of physics that govern the boiling of water in a kettle, the falling of an apple, the glow of a lamp, can be traced back to the first minutes and first thousands of years of cosmic history. The atoms in your body were once part of that early plasma, then that primordial gas, then clouds and stars and planets. The knowledge we have built is not separate from you. It is, in a very real sense, your own story, told on scales of time and distance that are hard to grasp, but strangely soothing to contemplate. If your mind feels full, you can let the details drift a little. Keep just the gentle shape of it, a universe that expands and cools, a fog that clears, a background glow that persists, structures that grow under gravity's slow pull, hidden components that shape what we see, even though we cannot yet touch them directly. That is the part we know, the part that rests on firm ground. On that foundation, later, we can safely ask bolder questions about what might lie beyond the first frame. For now, you can simply breathe and let the thought of this long, orderly unfolding keep you company as you rest. There is a moment in this story where even the calmest scientist has to stop and admit, very quietly, that our tools fail us. Up to a certain point in cosmic history, we can write down neat equations, solve them, compare the answers to what we see in the sky, and feel a kind of deep satisfaction. But if I keep walking backwards in time along that mathematical road, there comes a sharp cliff. The symbols on the page rise to infinity. Curves in space-time twist too tightly. Quantities we usually treat as smooth and well-behaved blow up without warning. That cliff is what we call the Big Bang singularity, and it marks the great barrier in our understanding. To see why this happens, I have to invite you into the logic of general relativity for a moment, but gently, like leading someone down a dim corridor with a small lantern. In Einstein's picture, gravity is not a force that pulls objects together through empty space. It is the bending of space-time itself by energy and mass. A planet orbits a star because the star's presence curves the geometry around it, and the planet simply follows the straightest available path through that curved geometry. If you give me the distribution of matter and energy, general relativity tells me how space-time curves. If you give me the curvature, the theory tells me how matter moves. When cosmologists apply this framework to the entire universe, they make an assumption called homogeneity and isotropy. Those are fancy words for roughly the same everywhere, and roughly the same in every direction, once you average over very large scales. Under that assumption, the geometry of space can be described by a single scale factor, a kind of global measure of how big the universe is at a given time. If that scale factor grows, the universe expands. If it shrinks, the universe contracts. The famous Friedmann equations link the evolution of this scale factor to the total energy density of the universe. Now, if I run those equations forward in time, from a hot, dense beginning, they describe an expanding universe that cools, forms atoms, forms stars and galaxies, and eventually reaches the present day. If I run them backward from the present, they tell me that the scale factor must have been smaller in the past, that the density of matter and radiation must have been higher, that the temperature must have been more extreme. So far, that lines up beautifully with the evidence we see in the cosmic microwave background and the abundances of the light element. The equations and the observations sing the same tune. But if I keep going, not just to very early times, but to the very first instant, something peculiar happens. The scale factor in the simple solutions of these equations goes all the way to zero at a finite time in the past. When that happens, the density of matter, which is basically the amount of energy per volume, goes to infinity, because you are trying to squeeze a finite amount of energy into a volume that shrinks to nothing. The curvature of space-time, which depends on energy density, also goes to infinity. These infinities are not just big numbers, they are signals that the description itself has broken down. At that point, we say there is a singularity. Not because we have seen it, not because we have a photograph of that state, but because the mathematics refuses to give us a sensible answer beyond it. The singularity theorems, proved by Hawking and Penrose and others, show that under very general conditions, if a universe like ours has been expanding for a long time, and the energy content obeys some reasonable rules, then there must be a past boundary where geodesics, the straightest possible paths in space-time, cannot be extended any further. That boundary is what we loosely refer to as the Big Bang singularity. It is tempting, especially in popular language, to imagine this as an actual physical point in the past where everything in the universe was compressed into something smaller than a dot. But as I lie here and talk you through it, I want to be very honest. In the strict language of physics, a singularity is a place where our theory stops being predictive. Beyond that point, the equations of general relativity do not tell us what happens. They simply end. The singularity is not a location inside space-time. It is the edge of the map. There is another way to think about this that I find both humbling and strangely peaceful. In general relativity, time is not a separate universal river that flows independently of everything else. It is one dimension of the space-time fabric, intertwined with space and shaped by the distribution of matter and energy. When we trace a path through space-time, we call it a world line. For any object, its world line is the history of its existence, a thread running from the past to the future. If that thread is cut off at some finite length in the past, then as far as the theory is concerned, that is where time begins for that object. If all possible world lines in, the universe can only be traced back a finite amount before they end at the singularity, then there is simply no before within that framework. It is not just that we do not know what happened earlier. Earlier, in a precise sense, does not exist in the geometry described by the theory. It is like asking for a location beyond the starting point of every path on a map when the map itself has no points beyond that edge. The question, what happened before the Big Bang, becomes, within pure classical relativity, a little like asking what lies north of the North Pole. It sounds reasonable because we are reusing familiar words, but it is actually self-contradictory. North is defined relative to the geometry of the Earth's surface. At the pole, there is no further north to go. Lying in bed at night, this idea can feel either liberating or frustrating. Liberating because it means we might not need to invent some earlier cause in time before time existed. Frustrating because our intuition is so stubborn. Our lives are full of chains of cause and effect, of memories stretching back, of stories with beginnings and middles and ends. It is hard to accept that at the largest scale, at the deepest level, the story might simply start at a certain page, with no prologue, not because the prologue is hidden, but because the book does not contain one. Still, general relativity is not the final word. It is a classical theory. It treats space-time as smooth and continuous, and it does not include the quantum nature of matter and fields. We know from many other experiments that at very small scales, quantum mechanics matters. Particles behave as waves, fields fluctuate, and there are fundamental limits to how precisely we can know certain pairs of quantities at once. There is a natural expectation that when space-time is curved, as tightly as it would be near the singularity, quantum effects in gravity itself must become important. The trouble is that we do not yet have a complete, experimentally tested quantum theory of gravity. To get a sense of the scale where quantum gravity should matter, physicists combine fundamental constants into special units, called Planck units. The Planck length is roughly the distance at which quantum and gravitational effects are expected to be equally strong. The Planck time is the duration light takes to travel that length. Written in decimal form, these numbers are incredibly tiny. In words, the Planck time is about a decimal point, followed by 43 zeros and then a 1 in seconds. Before roughly 1 Planck time after the Big Bang, our usual continuum picture of space-time is almost certainly inadequate. We are trying to apply a smooth canvas to a place where the canvas itself might be woven from discrete threads. So, when I talk about time zero, what I really mean is the limit of our current theory as we approach the Planck era. Our equations work very well from, say, a tiny fraction of a second after that early moment onward. They tell us how the plasma evolves, how nuclear synthesis proceeds, how recombination clears the fog, how structures grow. But as we push them beyond their domain of validity, past the Planck barrier, they give us nonsense, infinities, singularities, undefined behavior. That is not a description of nature. It is a description of our ignorance. This is why so many modern models of the early universe try to soften or remove the singularity. Some approaches, like loop quantum cosmology, suggest that space-time itself might be quantized, made up of tiny, discrete building blocks. In such models, when the density of the universe reaches a critical value, quantum effects produce a repulsive component of gravity, preventing the scale factor from shrinking all the way to zero. Instead of a singular beginning, the universe experiences a bounce, a transition from a previous contracting phase to the current expanding one. Time does not end at the bounce, it continues smoothly through, but the classical description changes. Other theories explore extra dimensions, string-like objects, or emergent spacetime, all trying in their different ways to answer the same question. How do we describe the fabric of reality when both quantum principles and gravitational curvature are too strong to ignore? Each proposal has its own mathematical elegance and its own challenges. None has yet been crowned by decisive experimental evidence. We are, in this sense, still in the exploratory phase, sketching possible bridges across the gap where our old road ends. As someone who loves both the firmness of data and the softness of night, I find it strangely comforting that science can be so clear about where it stops. The honesty of saying here our equations fail is not a weakness. It is a map of where new insight is needed. The singularity is not just a problem, it is a signpost. It tells us that the journey is not finished, that there is more to discover about how time, space, and matter weave together. For you listening now, perhaps with your body relaxing and your breathing settling into a slow rhythm, this barrier can serve as a kind of mental resting point. On one side lies the universe we can describe with confidence, from the first tiny fraction after the Planck time all the way through recombination and structure formation to the present day. On the other side lies a region of possibility, where different theories of quantum gravity paint different pictures, where before might mean a previous universe or a timeless quantum state, or something we have not yet learned to name. You do not need to decide which picture is right. Even cosmologists do not agree. What matters, for now, is the shape of the landscape. We have walked back along a well-lit path until the light fades, and we are standing at the edge of a vast, dim plain. We can feel that there is something beyond, but our current lanterns cannot show it clearly. Instead of that being a source of anxiety, it can be a kind of calm. Not every question needs an immediate answer. Some of them are allowed to remain open, gently tugging at the edges of our understanding, encouraging new generations to think differently. If your eyelids feel heavy, you can let the image of that barrier blur. Imagine time itself as a line drawn on a page, starting at some point and stretching onward. Our physics describes the part of the line to the right of that starting point very well. The part to the left, if it even exists, is simply not drawn yet. It is not printed in ink, it is blank paper. Somewhere, perhaps, a future theory will sketch in a new story there, with bouncers or cycles or quantum beginnings. But tonight, the blankness is allowed. It is part of the beauty. Later, in the next part of this journey, we will wander among some of the bold ideas that try to fill that blank space. Cyclic universes, big bounces, and strange quantum states that might have given rise to everything. For now, you can rest at the edge of what we know, aware that there is a barrier, aware that beyond it lies the unknown, and feel the gentle weight of that mystery settle around you like a soft, dark sky. The theories that tried to reach beyond the Big Bang were already strange, but there is something even more unsettling right here inside the universe we can see. The deeper astronomers looked into the sky, the more obvious it became that most of what exists does not shine, does not glow, and does not behave the way ordinary matter does. Long before anyone spoke seriously about multiverses or cosmic bouncers, careful measurements were whispering a simpler, more unnerving message. The familiar world is not the main ingredient. It began, in a quiet way, with the motion of stars in galaxies. If you measure how fast stars orbit around the center of a spiral galaxy, you can use basic gravity to infer how much mass is pulling on them. It is a straightforward calculation. More mass should mean faster orbits near the center, and slower ones as you move outward into the thin edges. The surprising thing is that this is not what the observations show. Instead of dropping, the rotation curves of many galaxies flatten. Stars far from the center move just as quickly as those closer in, as if they are feeling the pull of great amounts of hidden matter surrounding the visible disk. At first, that might sound like an error, a quirk of a few systems. But as more galaxies were measured, the pattern persisted. Clusters of galaxies showed a similar puzzle. The galaxies in them were moving so fast that, if only the visible matter were present, the clusters should have torn themselves apart long ago. Something unseen was binding them. Gravitational lensing, the bending of light paths by mass, added another layer of evidence. When distant galaxies are seen through massive clusters closer to us, their images are warped and magnified in ways that reveal how much total mass the light passes by. Time and again, those gravitational maps show more mass than all the stars and gas can account for. The simplest explanation is that there exists a form of matter that does not interact with light at all, or interacts so weakly that it neither emits nor absorbs radiation in any way we can currently detect. It reveals itself only through gravity. We call it dark matter not because it is spooky, but because it is invisible and unknown. According to our best fits to cosmic data, dark matter makes up roughly 1/4 of the total energy content of the universe. Ordinary matter, the atoms that build stars, planets, and bodies, contributes only a few percent. The rest belongs to something stranger still. That last ingredient, the largest slice of the cosmic pie, emerged from a very different set of observations. Astronomers studying certain supernovae in distant galaxies noticed that these stellar explosions, used as standard candles, were dimmer than expected. To make sense of this, they had to conclude that the universe's expansion has been speeding up for billions of years. Gravity, by itself, should pull things together and slow expansion down. To accelerate, the universe needs a component with a kind of negative pressure, something that pushes space-time apart. Einstein once introduced a similar term into his equations of general relativity, calling it a cosmological constant. In his time, it was meant to keep the universe static. When later evidence showed that the cosmos is expanding, he reportedly called that constant his greatest blunder. Yet the concept has returned. Today, a simple cosmological constant, the fixed energy density of the vacuum itself, fits much of the data. This mysterious component is called dark energy. It does not clump like matter. It seems to be spread smoothly through space, acting as a gentle but relentless pressure that accelerates expansion. When all the evidence is combined, the cosmic microwave background, the large-scale distribution of galaxies, the motions of clusters, the brightness of distant supernovae, a strange picture emerges. Only a small fraction of the universe's content is made of familiar atoms. Roughly 1/4 is dark matter, unseen but gravitationally active. Roughly 2/3 is dark energy, a smooth background that shapes the fate of cosmic expansion. The names dark matter and dark energy are placeholders, not explanations. They signify our ignorance as much as our knowledge. There is something almost poetic in this. Human eyes evolved to see a narrow band of light, enough to navigate a world of trees, rivers, and skies. Telescopes extended that vision to other wavelengths, revealing radio waves, infrared glow, ultraviolet flares, X-rays, and gamma rays. Each new band opened a new window on reality. Yet even with all those windows, we now know that most of what governs the universe does not show up in any of them. The visible cosmos is like the foam on the crest of a wave. The mass and motion lie beneath the surface. Dark matter might be made of some new kind of particle, possibly a weakly interacting massive particle that rarely collides with ordinary atoms. Enormous detectors deep underground, shielded from cosmic rays, sit in silence, waiting for the faintest tap of such a particle on a nucleus. So far, they have found nothing definitive. Other ideas link dark matter to ultralight fields, vibrating across galaxies, or to sterile neutrinos that barely feel any force at all. Every hypothesis is an attempt to turn the gravitational evidence into a more concrete picture, to connect the unseen scaffolding of the universe to the familiar language of particles and fields. Dark energy is even more elusive. If it is truly a cosmological constant, then it may simply be a property of space-time itself, the energy of the vacuum. Quantum field theory does predict such vacuum energy, arising from the restless fluctuations even in empty space. But when physicists try to calculate its value, they obtain a result that is absurdly larger than what is observed, off by many orders of magnitude. Reconciling that difference is one of the deepest unsolved problems in theoretical physics. There are also hints that dark energy might not be constant after all, that its influence could be changing slowly over cosmic time. Large surveys of galaxies and quasars, like the ones carried out by instruments dedicated to mapping the expansion history in detail, are beginning to test this possibility. It is here, in the interplay between these two dark components, that the question of the universe's origin and fate becomes more than an abstract thought. If dark energy remains constant, expansion will continue to accelerate, and distant galaxies will drift out of view, one by one, until only the local group remains. Stars will exhaust their fuel, black holes will slowly evaporate, and the cosmos will approach a cold, thin emptiness. In that picture, the infinite future of the universe becomes a quiet, sparse place, more like a dim whisper than a grand climax. If dark energy weakens over time, another destiny unfolds. Expansion might slow, perhaps even halt. Gravity from all the matter, both dark and ordinary, could begin to pull the cosmos back together. A long era of contraction might follow, with galaxies drawing closer, clusters merging, and temperatures rising. If that contraction continued far enough, the universe could end in a big crunch, a state of extreme density and heat that is in some ways a mirror image of the early fireball we call the Big Bang. In scenarios like loop quantum cosmology, the bounce from such a crunch could seed a new expansion, linking the end of one universe to the beginning of another. Even if dark energy never reverses, its nature might be tied to what happened before the beginning we can see. Some theories imagine that dark energy is a field, slowly rolling down a potential hill, and that the Big Bang occurred when that field changed state, like water that suddenly freezes or boils. In those models, the nothing before the Big Bang is not absolute absence, but a more subtle quantum vacuum poised on the edge of transformation. The energy locked in that vacuum becomes the fuel for inflation and the later expansion we observe. Dark energy, in this view, is not an add-on. It is the residue of the process that birthed the visible universe. Dark matter, too, may carry clues from a deeper past. If its particles were created in the early hot plasma, their properties, mass, interaction strength, abundance, might encode the temperature and density of the universe in its first moments. Different models of pre-Big Bang physics predict different kinds of relics. Some might leave faint imprints in the cosmic microwave background or in the pattern of how galaxies cluster. Others might show up as subtle distortions in gravitational wave signals. In a sense, dark matter and dark energy turn the entire cosmos into an experiment, whispering about conditions and laws we cannot recreate in any lab. There is a gentle irony in all this. The components that make the universe so hospitable to stars, planets, and life are, in part, the ones we do not yet understand. Dark matter provides extra gravity that helps galaxies form quickly and remain stable. Without it, structure might grow too slowly, or not at all in the time available. Dark energy, by accelerating expansion, may prevent the universe from recollapsing too soon, leaving enough cosmic time for chemistry and biology to unfold on small, rocky worlds around calm stars. Whether that balance is an accident, a necessity, or an echo of deeper principles is an open question. If you picture the universe now, try to imagine it not as a static black canvas sprinkled with points of light, but as a living fabric held in tension between these unseen influences. There is the pull of dark matter, shaping the skeleton of cosmic structure. There is the push of dark energy, stretching space-time itself. And embedded within that vast dynamic balance are islands of light and chemistry, where atoms assemble into molecules, molecules into cells, cells into minds capable of asking why any of this is so. Thinking about these invisible elements does not require tension or strain. It can be more like listening to distant waves while lying on sand. You do not need to resolve every detail to feel their presence. It is enough to know that the night sky you might glimpse from a window or imagine behind closed eyes is only the visible trace of a much larger design. Something holds galaxies together. Something drives them apart. Both somethings are still mysteries. Both are active right now, at every point in space. From here, the path curves naturally back toward our original question. If most of the universe is made of things we cannot see, and if those things govern not only the structure and future of the cosmos, but perhaps its very origin, then the idea of nothing before the Big Bang becomes even more subtle. The vacuum itself may be rich with potential. The darkness between stars may be full of substance. And the unknowns at the largest scales reflect the unknowns at the very beginning. Once we accept that the universe may have started from a state we do not yet understand, and that it is filled with ingredients we can feel only through their influence, what does that do to our sense of being here at all? How does a cosmos built mostly of mystery give rise to beings who crave clarity? Those are not questions that dark matter or dark energy can answer directly, but they are the questions that drift in behind them, like a soft tide following a distant storm. All the talk of dark matter and dark energy leaves a very strange taste in the mind. The more we learn about what fills the universe, the more obvious it becomes that the word empty does not really apply anywhere. Even the regions between galaxies, those vast gulfs that look black and bare in telescopes, are not truly vacant. And once you notice that, the old philosophical question, why is there something rather than nothing, starts to twist into a new shape. Before asking why there is something, we have to ask what nothing honestly means. In everyday language, nothing is simple. An empty box has nothing in it. A quiet room has nothing happening. When we say nothing, we imagine a kind of blankness, an absence you could almost paint as pure black. For a long time, people pictured the vacuum of space in a similar way. A neutral stage, a silent backdrop against which particles and forces go about their business. There are stars and galaxies, and then there is the void, something, and then nothing. Modern physics does not agree. In quantum field theory, every type of particle is an excitation of an underlying field that fills all of space. There is an electron field, a photon field, fields for quarks and gluons and neutrinos, even a Higgs field giving mass to certain particles. The vacuum is not the absence of these fields. It is their lowest energy state, their quietest possible configuration. But quietest in quantum theory does not mean still. It means constantly, restlessly fluctuating. This is one of those places where the universe behaves in a way that is almost impossible to visualize, but very precise in math. Even when a field is in its ground state, uncertainty principles prevent it from being perfectly flat and motionless. Instead, it jitters. Energy briefly appears and disappears. Pairs of virtual particles blink in and out of existence, borrowing energy for a time shorter than a blink of an eye, then returning it so that no conservation law is ultimately broken. If you think of the vacuum as a calm ocean, quantum theory says that, seen up close, the surface is alive with tiny ripples and bubbles, constantly forming and fading. This is not just poetic language. There are real experiments whose results can only be explained if vacuum fluctuations are taken seriously. One famous example is the Casimir effect. If you place two uncharged parallel metal plates very close together in an otherwise empty vacuum, They feel a small but measurable force drawing them together. There is no obvious source for this force. No electric charge, no classical field pushing or pulling. The explanation comes from the quantum fields in the space around them. Between the plates, only certain modes of vibration of the electromagnetic field are allowed because the metal boundaries impose conditions on the waves. Outside the plates, more modes are possible. That imbalance in modes leads to an imbalance in vacuum energy, and the plates are nudged together as the system tries to minimize its overall energy. The force emerges from what we once would have called nothing. At the cosmic level, the energy of the vacuum may be directly linked to what we call dark energy, the mysterious pressure accelerating the expansion of the universe. In simple models, the vacuum has a tiny but non-zero energy density. Spread evenly through all of space, this energy acts like a constant push, stretching space-time ever more rapidly as the universe grows. It is as if empty space itself has a tendency to swell. The details are still under active investigation, and there is a massive mismatch between naive calculations of vacuum energy and the small value suggested by observations. But even that mismatch carries a message. Whatever nothing is, it is not simple. There is another twist. Many theories of the early universe involve the idea of a false vacuum. In that picture, the vacuum state before the Big Bang was not the true lowest energy state, but a kind of metastable plateau. The fields filling space were balanced on a ledge, not yet rolled down into the deepest valley of their potential energy landscape. You can picture this by imagining a ball sitting not at the bottom of a bowl, but on a small flat shelf partway up the side. It is stable for a while. If undisturbed, it could sit there for ages. But a tiny nudge could send it rolling down into a lower energy state. In cosmological models, a false vacuum can end in a violent phase transition. The field decays from its metastable state to a more stable one, releasing energy in the process. That released energy can drive a period of rapid expansion, very similar to inflation. It can fill space with hot radiation and particles. In some versions of this story, the Big Bang is exactly such a transition. The before is not an absence of everything, but a peculiar kind of almost nothing, a featureless vacuum with high energy density, poised on the edge of transformation. In that sense, nothing might be unstable. A pure, perfectly symmetric vacuum could be a state that cannot help but create something. Tiny quantum fluctuations could trigger bubbles of new phase, pockets where the field has changed value. Those bubbles would expand at high speed, their interiors becoming hot, dense regions filled with particles, which then evolve as new universes. The nothing that came before is not a clean slate, but a field-theoretic laboratory, primed for spontaneous creation. Some cosmologists, like Alexander Vilenkin, have used this language to suggest that the universe might have arisen from nothing in a quantum tunneling event. The idea is not that there was literal absolute nothing and then magic. It is that the laws of quantum gravity might allow a tiny closed universe to appear from a state with no classical space-time at all, much as particles can appear from the vacuum in other quantum processes. The details are subtle and still speculative, but the guiding thought is clear. In quantum theory, the vacuum is an active player, not a passive background. Once you accept that, the philosophical question becomes more nuanced. Instead of asking, why is there something, rather than nothing, you start to ask, what kind of nothing would be natural? And do the laws of physics themselves demand that something must exist? If the vacuum is inherently restless, if fields cannot help but fluctuate, then perhaps the emergence of structure is not an accident, but an intrinsic property of reality. Perhaps the most fundamental state is not a dead, featureless void, but a seething possibility. This does not answer every concern. One can still ask why the fields exist at all, why the laws have the form they do, why the vacuum has this structure and not another. Those questions may point beyond the reach of physics as we currently practice it. But even without resolving them, recognizing the richness of the vacuum changes the emotional flavor of nothing. The word becomes less like a hard wall and more like a foggy horizon, a place where our usual categories blur. Lying with that thought for a while, you begin to see a pattern that stretches from the smallest to the largest scales. In the brain, a moment of silence is not a blank record. Neurons continue to fire quietly, memories replay beneath awareness, patterns form and dissolve in the background. In the universe, a patch of empty space is not a glassy static void. Fields vibrate, particles wink in and out. Virtual excitations trade energy in the shadows. Even sleep, which feels like nothing when you look back at it from waking, is full of cycles and invisible work. Memories consolidating, hormones balancing, damaged molecules being repaired. Nothing, it seems, is often just something we do not notice yet. Thinking about pre-Big Bang scenarios through this lens adds another layer of calm strangeness. If time itself is born in the transition from a quantum vacuum into an inflating space-time, then asking what happened before might be like asking what happened before a melody starts when all you had was the still air in the room. The silence was not meaningless, it was the condition in which the music could arise. The fields in their vacuum state may be the silent air of the cosmos, carrying within them the capacity for rhythm long before any particular song is played. This way of looking at nothing does not settle the debate between different cosmological models. It does not tell you whether our universe is one cycle in an endless chain, or one bubble in a multiverse, or a unique event. What it does is soften the conceptual edge of the question. There is no sharp cliff between nothing and something. There is a spectrum, a gradient from quiet to loud, from symmetric to broken, from uniform field to structured world. When you reflect on that gradient, the line between cosmos and consciousness blurs a little. The thoughts passing through your mind arise from the activity of neurons, which rely on molecules, which rely on atoms, which were made in stars, which formed in galaxies, seeded by quantum fluctuations in a field-filled vacuum. The chain of emergence runs all the way from the jitter of nothing to the feeling of I. At no step along that path is there a perfect emptiness. There is always a background, there is always a field. Perhaps nothing, in the strict philosophical sense, never existed at all. Perhaps reality has always been some kind of something, even when it was only a quiet quantum sea. That does not remove the wonder. If anything, it deepens it. Instead of a single miraculous jump from void to universe, you have an unbroken continuity of being, a long, slow unfolding from the simplest possible state to the richly structured world that you inhabit now. You do not need to picture every step. You do not need to grasp every equation. It is enough to know that even the darkest regions, even the so-called emptiest spaces, are part of a living fabric where silence is full of potential. From that perspective, the question is not why there is something instead of nothing, but how astonishing it is that the something includes you, here, able to lean back into the darkness and let your thoughts drift over edges that were once called nothing at all. By now, the story has carried you from the hot, crowded beginning of the cosmos to the quiet restlessness of the quantum vacuum. Along the way, familiar words have been quietly rewritten. Empty space turned out to be full of fields. Darkness turned out to be crowded with unseen matter and a gentle outward pressure. Even nothing started to look more like a low humming background than a clean, sharp absence. Once all of that sinks in, the question floating at the edge is no longer only about physics. It becomes something softer and more difficult to phrase. Given everything we do know, what lies forever beyond our reach? Modern cosmology is remarkably successful inside its domain. It traces the expansion of the universe across billions of years. It predicts the pattern of light in the cosmic microwave background. It explains why there is more helium than any star could have built on its own. It shows how galaxies gather along filaments, how clusters form at their intersections, how the great cosmic web stretches from one horizon to another. Inside that web of explanations, there are still loose threads, yet the fabric holds. It is not guesswork. It is a network of ideas tested again and again against what the sky actually shows. But every theory has boundaries. General relativity breaks near the Planck scale, where space-time itself may need a quantum description. Quantum field theory works beautifully in flat space-time and in gentle gravitational fields, but has not yet been fully merged with curved geometry in a complete way. At the fringes of those two great pillars, the questions about origin and ultimate fate sit like faint constellations, clearly visible, yet too far away to touch. One limit comes from observation itself. Light moves at a finite speed. The universe has a finite age. That means there is a cosmic event horizon beyond which no signal has had time to reach us. Even if space extends infinitely, the region that can ever influence us is bounded. Galaxies whose light has not yet arrived are already beyond contact. In a future dominated by dark energy, even more of the cosmos will slip away. Distant galaxies will be carried out of causal reach, their signals forever unable to cross the ever-growing gaps. Any beings living in such a remote time, with only a small cluster of galaxies visible, would reconstruct a very different story of the universe. They would read a smaller book. Another limit is more subtle. Even inside the observable universe, the information we can retrieve about the earliest times is filtered by physical processes. Before the epoch of recombination, photons were trapped in the hot plasma. The microwave background is the oldest light we can see directly from a universe a few 100,000 years old. Anything that happened before that is hidden behind a wall of scattering. Neutrinos and gravitational waves could, in principle, carry information from earlier epochs, but they are incredibly hard to detect with the precision needed to decode the fine details of pre-Big Bang physics. There may be faint signatures in the polarization of the microwave background or in the stochastic background of gravitational waves, yet even those are filtered remnants, not sharp images. A third limit lies in the nature of probability and initial conditions. Cosmological models describe how particular starting states evolve. They do not always tell you why one starting state was realized and not another. Inflation, for example, smooths out many details of whatever came before, wiping away irregularities like a long expanding breath smoothing ripples on a pond. That smoothing is part of its power, but it also hides the specifics of earlier history. Different pre-inflationary scenarios can lead to very similar observable outcomes. From our vantage point, many distinct beginnings may be observationally indistinguishable. No matter how carefully we measure, the data might never single out one unique origin story. At this point, the line between physics and philosophy becomes thin. If certain questions are undecidable in principle, if no experiment, even in theory, could separate one answer from another, then some cosmologists argue that those questions do not belong to science at all. Others feel that the boundary is fuzzier, that aesthetic criteria like simplicity, coherence with deeper theories, or the ability to unify disparate domains still have a role to play. When several models make the same predictions for everything we can measure, they can still differ in how they fit into a broader landscape of ideas. This raises a gentle but important fact. Even in a fully scientific story, choices of language and framing matter. Calling the earliest moment a beginning invites one kind of intuition. Calling it a transition invites another. Describing the vacuum as nothing encourages certain images. Describing it as a ground state suggests others. None of these words are wrong, but each carries emotional weight. The same equations can sound very different depending on whether they are presented as a singular creation or as one phase in an ongoing pattern. Philosophers of science have long pointed out that theories are not just collections of equations. They are also narratives about which aspects of the world are taken as fundamental and which are seen as emergent. In some views, space-time itself might be emergent, arising from more basic quantum entanglement patterns or information-theoretic structures. In that picture, asking what happened before, space-time would be like asking what happened before a story in a book, when the book itself did not exist yet. The words on the page have a beginning, but the deeper substrate, the paper, the ink, the language, preceded that particular arrangement. On the human side, there is another horizon that cannot be ignored, the limits of our own cognitive tools. The brain evolved to handle days and seasons, rocks and rivers, the social dance of small groups. It did not evolve to be comfortable with 10 dimensions, non-local entanglement, or timescales of tens of billions of years. Yet here it is, stretched across those scales by mathematics and imagination. There is a real possibility that some aspects of ultimate reality are not just unknown to us now, but in principle ungraspable in direct intuitive terms. We may only ever interact with them through symbols, indirect clues, and carefully constructed analogies. That sounds discouraging at first, but it can also be a kind of relief. You are not failing if the idea of a timeless quantum state that gives rise to time feels slippery. It is slippery. You are not missing something obvious. If you cannot decide whether the universe came from nothing or from something more subtle, the people working at the forefront of these questions wrestle with the same discomfort. Their advantage is not that they feel no confusion, but that they have learned how to work with it, to channel it into precise questions and testable consequences wherever possible, and to leave the rest open without panic. There is, hidden in this, a quiet lesson about living with uncertainty. Cosmology shows that it is possible to know a great deal and still face a horizon of mystery that does not shrink. Each time a new telescope is built, it fills gaps in the map, but also reveals deeper gaps beyond. Each time a theory is refined, it explains more phenomena, but also raises sharper versions of questions once hidden in vagueness. The unknown does not retreat in a straight line. It rearranges itself, sometimes moving closer, sometimes farther, always present. You might notice a similarity with personal questions that never quite resolve. Why am I here? What should I do with this finite life? How do I live in the face of time and change? No scientific model can answer those on your behalf, yet the cosmological story can influence how they feel. Knowing that the universe is older than any story humans told, that stars lived and died before Earth cooled, that space itself is stretching, can make individual worries feel smaller. At the same time, knowing that every atom in your body has traveled a 14th billion year journey to arrive here can make your choices feel strangely significant. You are a brief configuration in a very long experiment. Standing at this philosophical horizon, one can respond in many ways. Some people weave the scientific picture into a spiritual or religious framework, seeing in the laws and patterns a reflection of deeper purpose. Others embrace a secular awe, finding meaning in the fact that a law-governed universe, with no external intention, has nonetheless generated beauty, complexity, and the capacity for kindness. Some focus on the sheer improbability of consciousness arising at all and take that improbability as a call to pay attention. From a strictly cosmological standpoint, no particular meaning is mandated. The universe does not announce a reason for existing in the same way a book's author might state a theme, yet the absence of a dictated meaning leaves room for creation. In the same way the early universe allowed small fluctuations to grow into galaxies and stars, your life allows small intentions to grow into relationships, projects, and stories. The physics does not tell you what those should be. It simply provides the stage on which they can happen. Remember too that not knowing everything does not negate what is known. The fact that we cannot peer behind the Big Bang with current theories does not erase the evidence for a hot, dense early state. The fact that dark energy's exact nature is uncertain does not cancel the clear signs of accelerated expansion. The horizon of ignorance is not a wall erasing the landscape. It is a boundary marking where maps currently end. Beyond it, the terrain is not empty, only uncharted. If you hold that image gently, a map spreading out across a world, with detailed coastlines in some regions and blank spaces in others, you might notice a subtle shift inside. The unknown stops feeling like a threat and starts to feel like an invitation, a place where future minds, maybe very different from ours, will one day roam, a space for questions you have not yet formed. The universe seen this way is not a puzzle that must be fully solved to be worthy of wonder. It is a living field of partial answers and open possibilities. And in the midst of that field sits one small, quiet fact. Right now, on a single planet, orbiting a single star, in one galaxy among many, you are here, aware of all this enough to think about it at all. That awareness may be brief, it may be limited, but it is real. It is part of the story. The horizon of what cannot yet be known surrounds you, and yet inside that circle, there is already more than enough to fill a lifetime of reflection. The story of the universe doesn't end with a bang or a whisper, but with a breath. Not the kind that begins or ends something, but the one that rests quietly between them, the pause that holds both motion and stillness. If you followed this journey from the beginning, from that first impossible spark of time through the dense fog of the early cosmos, across the invisible scaffolding of dark matter and the expanding tide of dark energy, through the trembling fields that never quite sleep, then you have already crossed the longest distance any mind can travel. You've gone from wondering what came before the universe to realizing that perhaps the question itself was part of the universe learning to speak. Every step along this path has peeled away one illusion. Space was not empty, it was alive with geometry. Matter was not solid, it was woven from probabilities. Nothingness was not void, it was restless potential. Even time, the quiet current carrying galaxies and thoughts alike may not be fundamental, but something that rises and falls from deeper rhythms, still unseen. The universe has not merely expanded in size, it has expanded in meaning. The more we've learned, the less separate we've become from it. The farther we look, the more it begins to look like us, or rather, the more we begin to look like it. When astronomers gaze at the faint light of the cosmic microwave background, they are not only looking back in time, they are looking at a kind of cosmic memory, a snapshot of everything that would one day give rise to the world you now inhabit. In those faint fluctuations, in the tiny unevenness of the primordial plasma, were written the seeds of galaxies, of stars, of worlds, of oceans, of lungs, of minds. From the first irregularities in that fireball, every future pattern, every breath, every thought, every word was already waiting to unfold. You are in the most literal sense, one of those ripples made conscious. And so, when you look outward into the night sky, you're not really looking away from home. You are looking through layers of your own origin, through time, through light, through the patient architecture that makes existence possible. Those photons that left their stars billions of years ago have crossed gulfs of expanding space, only to end their journey in your eyes. In that moment, the distance collapses. The observer and the observed, the question and the answer, the beginning and the continuation all merge into one. If the Big Bang marked the moment when time and space unfolded, then consciousness marks the moment when the universe folded back to look at itself. Through you, it feels its own temperature, tastes its own chemistry, dreams of its own past. The equations may tell one story, the observations another, but beneath both runs a current of intimacy, the idea that knowing the cosmos is not something we do from the outside, but something we participate in. We are not guests in this vastness, we are expressions of it. And that realization changes the tone of every earlier question. What came before the Big Bang becomes less an interrogation of absence and more a meditation on continuity. If before and after are human conveniences, maybe existence itself doesn't follow our verbs. Maybe it just is eternal motion without a starting line, a wave without a source. The physics, of course, will keep refining its models: cyclic universes, quantum bounces, multiverses, false vacuums. But behind every theory, there will still be this quiet astonishment that anything exists at all and that it's beautiful enough to study. Science at its best does not shrink mystery, it refines it. It teaches us to see darkness, not as the absence of light, but as the presence of everything we have yet to understand. Every time a telescope peers deeper, it finds more galaxies instead of edges. Every time a particle accelerator smashes smaller, it finds more structure instead of nothingness. There's a lesson in that repetition, a reminder that the quest for knowledge isn't a race to an ending, but an expansion of belonging. The universe is not holding its secrets out of reach. It is unfolding them slowly, like dawn. And in that slow unveiling, there's something almost tender. The cosmos doesn't owe us comprehension. It doesn't need to explain itself to the creatures made from its dust. Yet, somehow, it does. It leaves clues in starlight and gravity, in fossils and DNA, in the shape of a snowflake and the curvature of space-time. It leaves the same mathematical fingerprints on the spiral of a galaxy and the hall of a seashell. It has written its autobiography in everything that exists and invited us to read it, not with urgency, but with wonder. So perhaps in the end, the greatest answer to how did nothing exist before the Big Bang is not an equation or a theory, but a perspective, that the line between nothing and something was never sharp. The universe may have always been humming quietly, waiting for awareness to join the song. And once awareness appeared, once it began to listen, the silence of the cosmos became music. You are part of that music. Every heartbeat, every breath, every thought is a rhythm played on the strings of space-time. Every time you look up at the stars, you are hearing the echo of creation. There's a kind of peace in that realization, not the peace of resolution, but the peace of participation. The universe doesn't ask you to solve it tonight. It only asks that you notice it, the way light bends through air, the way gravity shapes a wave, the way even in darkness there's texture, depth, quiet motion. Those are the small windows through which the infinite becomes personal. Through them the cosmos whispers, "You belong here. You always have." If you let that whisper settle in, the mind begins to quiet. Questions still exist, but they lose their edges. The same space that once felt cold and distant becomes something gentle and familiar. The same nothing that once seemed terrifying becomes a cradle of potential. And as your awareness softens, not disappearing, just expanding, you begin to feel what the universe has been saying since the very beginning, that you are made of the same light that first broke through the fog, the same energy that once flickered out of a silence so deep it can still be felt. In that realization, there is both science and serenity. The equations may never close the circle, but they trace its outline well enough to rest inside it. You do not need to know where time began to feel at home in it. You do not need to see the edge of the cosmos to know you're within its story. The mystery that began with nothing has already given you everything: stars, thought, love, breath. The rest can wait. So close your eyes, not as an escape from reality, but as a return to it. The same darkness that hides the galaxies will cradle your own thoughts now. The same silence that surrounded the first atoms still hums softly in your chest. And as the last traces of the day dissolve into the quiet between one heartbeat and the next, remember, the universe never stopped creating. It's doing it even now, through you, through this moment, through the small, luminous act of simply being.